Right, so I've got, there are actually two different, no, how many I've made? There are two different sheets, so give you these tables. I've got to bring them at once and table. Right, it's 1 o'clock, so let's start. We have quite a lot to do today, but if there's anything you don't understand or anything like that, then ask please. The first thing is the homework, then we look at some games that are not zero-sum games, you can't, where there are possibly situations where both players can benefit from doing something, and then in the end we'll have a quick look at the game theory exam questions from last year. That's the plan. We can do all that by 2 o'clock and we'll be very happy. Just very briefly, has anybody got a solution to this homework question? The first question asks you to find a Nash equilibrium for the rock, paper, scissors game, and I think it's quite. What you would expect, of course, is because none of the three possibilities that the players have, rock, paper, scissors, are somehow better than the other, then you probably would expect the optimal mixed strategy to be 1/3 probability of each of the three options, and that also turns out to be the Nash equilibrium. So there's a Nash equilibrium where one player plays 1/3, 1/3, and 1/3 for each of the rock, paper, scissors. It doesn't really matter if they're all the same. And the other player also plays 1/3, 1/3, 1/3. The Nash equilibrium. Now you can find it in the linear programming way that we did last week, or you can do some tricks and prove that it's a Nash equilibrium, or not to do that. Just because we don't have the time. And the second one is similar. So here, I don't think you can guess the. You probably cannot guess what the Nash equilibrium or a Nash equilibrium is going to be. So if you do the LP, as we did described in the book as well, and as you're doing in your assignment, and if you solve it, then you get that the blue player, at least that's what I got, should play B1 with probability 2/3 and B2 with probability 1/3, and the red player should play R1 with probability 2/3 and R2 with probability 1/3 and R3 with probability 0. But possibly there are other equilibria. I haven't quite checked that thoroughly. So this is definitely one that comes with the linear program. So if the linear program has several optimal solutions, then each of them is going to be Nash equilibrium. Good. So here you can say that the value of the game is 1/3. So the blue player is going to be winning. And so here the value for rock, paper, scissors is 0. So it's a fair game. If the players keep playing truly randomly, then no one is going to be winning in the long run. So the question is, why are there world championships in rock, paper, scissors? And the answer is that people are not really able to play really randomly. And so they will put some patterns in, and the other players are trying to find the pattern in the way that people are playing, outsmart them. But if we're playing truly randomly, like really randomly, then it wouldn't be possible to be in the long run. Okay. Any questions about the homework? No. Now you can put 1 or 2 or not, depending on how many questions you solve on the register. Thank you. And next thing we're doing is non-zero sum games. Okay, so this game is presented in a gender-neutral way here, because usually it's well, quite often this example appears in the literature as the battle of sexes, BOS. So battle is also BOS, and the two friends are actually a couple in that version, and the guy wants to see some football or something, and the girl would want to go to the cinema. So, but this is a better version. There's no distinction. I have no stereotypes. And this is, you can see, kind of, I mean, you probably see that this is a non-zero sum game, because not that. So it's not that, like, if one of them wins, the other guy loses, and vice versa. It's that if they both go together, that's for both of them, it's preferable to going separately. Okay? So you can't put it as a zero sum game. And the possible payoff matrix will be, so the Bach player. Okay, so they have two strategies, to go to see Bach and just go to see Stravinsky. And Stravinsky player also has these two strategies. And one possible payoff matrix is one where, well, so the two people going to two different concerts is not very good for any one of them. They're not going to enjoy themselves very much. And yeah, the Bach player is really, really happy, and the Stravinsky player is somewhat happier than before. And they go to see Stravinsky, and the Bach player is somewhat happier than before, and the Stravinsky player is happier than before. Okay, so remember that in the payoff matrix, we have these payoff as the first thing in the pair, and the second one is the column players, so F's payoff. Okay, so the 2 here is how much that player likes it, and the 1 here is how much that player likes it. Okay. Now, you've probably been able to deduce from what we've been doing here is that what we really want to do when we see a game is to find at least one Nash equilibrium, or possibly all of them. Right. So the question here is there a Nash equilibrium in this game? Can you find one? Is there any spare handouts? Can you please send them down here so that the people who are arriving late can also get them? Thank you. See that there's enough density for it. Okay, has anybody found the Nash equilibrium? No? No? Okay, you haven't found the Nash equilibrium, I'll give you one. So each of the players going to see back is a Nash equilibrium. Why? Well, because none of them can improve their payoff by going to see Stravinsky. Okay? So, changing what they do. Why? Well, if they are both here, then if the row player changes, their payoff is going to go down from 2 to 0. Okay, so they're not better off. So the row player, by switching from D to S, does not improve their odds. Or their, not odds, but you know what I mean, their payoff. Okay, and it's the same for this player. So currently their payoff is 1, but if they go to the other concert, their payoff is going to go down to 0. So they don't want to do that. Now, of course, you have to remember that where before we had only the payoffs for the row player and the payoffs for the column player were the negatives. We can't do it in non-zero-sum game, so we have to put them separately. So we're back to those players wanting their payoff to be as large as it can be. So there's no, the column player is no longer minimizing anything. They're both trying to maximize their payoff. So this is one Nash equilibrium in which well, the row player is very happy, the column player is somewhat happy, but they can't improve by doing something else unless the other player also does something else. In fact, there's another one, is that they both go to see Stravinsky. Then, kind of similar. So, in here, they're both going to see Stravinsky. The row player's payoff is 1, but if they switch to going to back, it goes down to 0, so they don't want to do that. And the column player's payoff is 2, and if they switch to the other concert, it goes down to 0, so they don't want to do that. Okay. Now, of course, the question is, how do you find the Nash equilibrium? And the answer is, it's quite hard. So if you have a small game like this, and somebody asks you to find a Nash equilibrium, what you can do is you can try all the 4 possible action profiles of pure strategies and see whether each of them is a Nash equilibrium. You can see that this one is not BS because both players can actually improve. So the row player can go from 0 to 1, and the column player can go from 0 to 1. So they're not going to settle on this, and they're not going to settle on this. But they might settle to. Okay. So is there any other Nash equilibrium there? I think there isn't one. Do you think there is another one? What you didn't quite think through is so this is okay. So B algorithm. So how about B goes to the back concept with probability 2/3 and Stravinsky with probability 1/3, and the other friend goes to back with probability 1/3 and Stravinsky with probability 2/3. But that's an interesting idea. Is this a Nash equilibrium? Right, if we want to show that this is a Nash equilibrium, we have to prove that none of the players can improve their expected payoff if the other players stick with their strategies, okay, with their probabilities. Okay, so for example, to prove it's Nash equilibrium. So we suppose that the player prefers Stravinsky has the mixed strategy that they have. So 1/3 for Bach and 2/3 for Stravinsky. And can the other player do better by picking something else than 2/3, 1/3? So can the improve? So let's say B has P and 1 minus P. So with probability P, they will go to see Bach, and with probability 1 minus P of the rest, they're going to see Stravinsky. What is the expected payoff? Okay, so the expected payoff. So with probability P, what's the expected payoff? Well, with a certain probability, the payoff will be 2. And with a certain probability, the payoff will be 1. And then with the remaining probability, it will be 0. So the expected payoff is 2 times the probability that they both go to see Bach, plus 1 times the probability that they both go to see Stravinsky. Now, the probability that they both go to see Bach, well, so what is that? So it's 1/3 because S has to go to see Bach times B. So this is times B. And the probability that they both go to see Stravinsky, well, it's 2/3 for this player times 1 minus P. So what is this? That's 2/3 no matter what the P is. Correct? Okay. Well, so that means that they just they're doomed. Like their expected payoff is going to be 2/3 no matter what genus do. You can put the probabilities no matter how you want. But because of these probabilities, your expected payoff is going to be 2/3. So you can't improve. And if you did the calculation for the other player, you get the same result. The other player also can't improve. So this is a Nash equilibrium. Who's confused now? Okay. Why? What exactly is confusing? Okay, so there can be several things that could be confusing. One of them is the notion of the Nash equilibrium. Okay, so that really is, I think we've done a couple of examples now, so it should be intuitively clear what the definition means. And it means that you have some strategies. So in this case, there are mixed strategies, and the Nash equilibrium is a situation where, when you look at every one of the players and you fix what all the other players are doing. So in this case, there are only 2 players, so you look at that player at the top, the row player, and you fix what, so if you're assuming that the other player is sticking to their probabilities and not changing them. Okay? And in this situation, where the second player has these probabilities, the first player, B, cannot change their probabilities and get a better expected payoff. Okay? So B cannot improve what they're earning. And also, if you now fix what B is doing, then S cannot improve. So no matter how they change their probabilities, they won't be getting a higher expected payoff than they are now. Okay? That's the notion of a Nash equilibrium. Is that clear? Now, the second thing that might look confusing is, so no matter what B does, okay, no matter the probabilities B picks for the 2 different strategies, the expected payoff of B is going to be the same. Now, does that mean that no matter what they do, it's always going to be a Nash equilibrium? Well, no, it doesn't. And the reason it doesn't is that if B changes these probabilities, then given that this is fixed, they're not improving their payoff, but if they change their probabilities, then the other player could change theirs and do something better. Okay? So you would, so in fact, it's important that it's 1/3 and 2/3. You can't just put something else there, because if you did, then the other player could be better off by doing something different. In other words, you can't deviate from, so you can deviate from your 1/3 and 2/3 as long as the other player is sticking to it, but if you do deviate, then the other player will do something different, and you're no longer having that. Okay, that's the best way I can explain it. Shall we move on? I think the kind of last thing, last new thing is this, which is we have in your handout, we have this article from the New Scientist, well, just over 2 years ago. And that's the classical example of a zero-sum game, non-zero-sum game, sorry, a two-player game. We've got some time to biometrics. So, what kind of chaos matrix do we get here? So we have U, and we have compass. Those are the two players. And U doesn't necessarily mean it's U, it's just a link. What are the possible strategies for U? Yes. So, confess, or say, and for the accomplice, it's the same. So, confess or stay. Okay. So, if you stay silent, and your accomplice confesses, then you're locked up for 5 years. Okay? If both of you stay silent, then both of you walk free. Looks like a good deal. To say. So what happens if you both confess, you both go put to it, right? And what are the remaining numbers? What about here? somehow odd. I didn't think it through quite carefully. Okay, is there a Nash equilibrium? Yes?
Confess.
That's a Nash equilibrium. If both confess, that's a Nash equilibrium. That's a weird version. Anyway, so yeah, so this is a okay, but also there's another one. I think. Okay, so the problem is, what is the problem? Yes.
It's more obvious to both stay silent, because why would you both 2 years by saying this might as well stay silent?
Yes, but that is right. So you might both want to stay silent because that's a Nash equilibrium. So you don't want to change to -2, and they don't want to change to -2. This is also a Nash equilibrium, however, because you don't want to change to -5, and they don't want to change to -2. So now it comes to the theory of rational choice. So outside of maths. It actually turns out what economists and studied this game, well, real life situation that resembled this game, they found out that typical, so if you have several Nash equilibria, you don't know which one they're going to arrive at. I mean, you're kind of expecting that they're going to arrive at one eventually. It turns out that people usually arrive at the button. I suppose the reason is that people don't, because your accomplice can't be trusted. So, so you don't know. I mean, if you were sure that they're going to stay silent, then you'd also stay silent. But if not, then you've got the risk of going to prison for 5 years. They confess, and it's kind of an interesting. Perhaps outside of our mathematical analysis of these games, an interesting feature of humans that we kind of like to avoid the big risk. Okay. So this is why insurance actually works. So why would you go and insure your house? Roughly by speculation, by We're looking at the expected value of what you're getting. The value of the insurance is negative because the insurance company has to be making profits. So you're paying the insurance company, and they have worked out the probability that they will have to pay you something because the house burned down, and they still are making profit. So if your house burns down, then you get the money back and you can buy a new house. So you're not earning anything. If your house doesn't burn down, then you've lost the premium. And the premium you've lost is you've lost more than the probability, the expected probability that your house burns down times the value of your house. But people try to avoid large risks, so they behave in a slightly dirty way. So if they really just thought it through, as Philip is telling you in decision trees, they would never take this insurance. They would just hope that the house doesn't burn down. But in this case, it turns out that in reality, people usually tend to get business capitalism in these situations rather than that one, even though that one would be better for war. Okay. That was okay, any questions? Good. Okay, so the other sheet that we got is last year's question 5. So that data from summer 2017. Have you done any exam questions with Philip? Yeah, in the lecture. No? Yeah. So you probably know that the exam has 8 questions. And each of them are 20 marks each. And you have to do question 1 and question 2, and then pick 3 out of the remaining 1. Okay, that's the system. Well, if you solve everything, then only the 5 best questions count. But well, you get these marks. Question 1, that's question 1 is simplex. It's the kind of shoemaker problem. So producing something, and we did an example of that question thing in the last week before Christmas. So if you go back there, question 2 is some Philip stuff, so usually some finance, I think. And then the remaining doesn't add up, does it? It's not 3 out of 5, it's 3 out of 6. So I said 3 of the 6 questions, and Philip sets 3 of the 6 questions, and I like to mix it up a little bit. So it's not like this question is only game theory, and that question is only linear programming, and that question is something else. But I usually like to put parts like this, A, B, so that you couldn't get away with only learning a little bit. Well, you still can get lost, so not make it too easy. So for example, this was last year. There's no guarantee that it's going to be the same or similar this year. But anyway, the part A is some kind of simplex method, and that's not what I want to look at now. But part B, worth 15 out of the 20 marks, is again similar to the assignment. So if you do the assignment, then you're quite ready to get this question right as well. So let's just quickly have a look at some of these answers. The first bit is, are there any dominated strategies in here? So can you quickly find any dominated strategies on these numbers? I'll try to. It's a red card. Red card. No, Catherine.
What?
For reading girl card. Have you found the dominated strategy yet? No, you're reading girl card. Okay, anybody? Yes?
B2.
B2 dominating what? Okay. Yeah, I think so. So B3 is dominated by B2, or you can say B2 dominates B3. That is probably right, because 4 is more than 3. Minus 1 is more than minus 2. Minus 1 is more than minus 3. And 2 is greater than 0. So it's what's called strong domination. So strongly means that they're all greater than. Weak means that some of them are equal rather than just greater than. Is there any other domination? Yes?
Is R1 weakly dominated by R4?
Is R1, right here, R1 weakly dominated by which one's the same, by R4? I think it is. It's because 1 is greater than or equal to 1, so this one, 4 is greater than 2, 4 is 2. 3 is greater than 0, and 2 is greater than minus 2. Oh, it doesn't show. Okay. Can't fit everything in there. Any time? Okay, so that's correct. Now, Minimax. How does Minimax work? So one thing is you can, if you want, because R1 is dominated, and B3 is dominated, you can just disregard them and rest. But you can still also consider them if you want. Either way is correct. So what is the minimax analysis that we want to do here? We want to take the minimum of each row. Okay, so what's that? That's minus 0, minus 1. This one is minus 3 if you want to do. Minus 2. Do you agree? this is min. And what's the max on each column? What are the maxima?
4.
4 in the mic. Yeah.
3. 3. 2.
Yeah, that's great. So what's next?
Select the maximum.
Exactly. So the maximum is the larger one, so that's 0 here. And the minimum is the smallest one is the 2, so R4 and B1. So best strategies that are suggested by this min-max are, again, B1, R4. Is that right? You keeping an eye on me? Question 3, does the game have a settle point? No, why not?
Because the two values, the maximum of the rows and the columns are the same value.
Because the 0 is not 2. Yes, that's correct. So the maximum of the minima is not equal to the minimum of the maxima. No. Yeah, well, it isn't good. So what it means, or you could say as well, if you look at this point, so that's not an equilibrium. That's not an equilibrium because the blue player can improve by switching to B2, and also the red player in fact can improve by switching to R2. So it's not an equilibrium. An equilibrium that's coming from this min-max is called a saddle point. And you always get it from the min-max list. And if that doesn't give you an equilibrium, or doesn't give you a saddle point, then there is no equilibrium of pure strategies. So you go on to the linear programming formulation. And so for part 4, so for part 4, you want the linear programming formulation for the blue player, it says. So you have decision variables x1, x2, x4, and v. And these are the probabilities in mixed strategy. And this is the value. Okay. So I'm assuming everybody has been doing this for the assignment, so people kind of know how it goes. I've left out x3 because b3 is dominated, and so if you leave it there, which is also correct, then in the optimal solution you have to get 0 for that. But you don't have to put it in at all. And you get 3 constraints, R2, R3, R4 for each of these strategies. R2 goes down like this, so you get 0 times x1 minus 1 times x2 plus 3 times x4 should be greater than or equal to b. In R3 you get 3x1 minus x2 is greater than or equal to b. And the last one is x1 plus 2x2 minus 2x4 is greater than or equal to b. The objective is to maximize the value. And of course you need x1 plus x2 plus x4. You want them, because they're probability distribution, you want them to sum to 1. And all of them should be negative. And I apologize for that in a minute over time, but this is just a proof that in 13 minutes that we spend doing this, we can get 15 marks. So it's not too short. Any questions? All right then. After Easter, there's 1 week left. I will take the 2-hour block in the evening, and we'll do a couple more exam strategies, questions, something like that. So Philip is doing this 1 o'clock lecture. If I don't see you before the holiday, have a good Easter, and come back fresh and ready for the exam.